NENOMATICA, where mathematics meets YouTube excellence. In this lesson, we will practice cyclic permutation of variables and apply it step by step to a polynomial in 4 variables. Rule: cyclic permutation transforms an expression by rotating variables. Think of a rotation like A to B, B to C, and so on. Step 1. Understand cyclic permutation. Here is a simple 3-variable cycle. A goes to B, B goes to C, and C goes back to A. Rule: example of cyclic permutation. Step 2. Example: apply the cycle A to B, B to C, C to A. The expression a plus B squared becomes B plus C squared. Rule: inverse cyclic permutation. The inverse simply rotates in the opposite direction, like B to A and C to B. Step 3. Inverse permutation. Starting with B plus C squared, rotate backward. We return to a plus B squared. Rule: apply cyclic permutation to the given expression. Step 4. The given expression is x squared plus 3xy plus 4z squared. We will rotate the 4 variables in this order: x goes to y goes to z goes to t, and t goes back to x. Rule: first cyclic permutation. Step 5. Replace x with y with z, and z with t. We get y squared plus 3yz plus 4t squared. Rule: second cyclic permutation. Step 6. Apply the rotation again. We obtain z squared plus 3zt plus 4x squared. Rule: third cyclic permutation. Step 7. Apply the rotation a third time. We get t squared plus 3tx plus 4y squared. Step 8. Note: if we apply the cyclic permutation once more, we return to the original expression. Final result: the cyclic permutations of the expression x squared plus 3xy plus 4z squared with respect to x, y, z, and t are the following 4 expressions. Quick challenge: can you predict the next cyclic permutation before it appears? Pause and think for a moment. It rotates forward from x to y to z to t, and then back to x. In this lesson, we will build an intuition for cyclic expressions, what they are, and how to test them with clear examples. Definition of cyclic expression. A cyclic expression is one that stays the same when each variable is shifted to the next one in order, and the last variable wraps around to the first. For example, A goes to B, B goes to C, and so on, and K goes to A. Step 1. Definition. An expression in variables A, B, C, and so on up to K is cyclic if after the first cyclic permutation, the expression is unchanged. Let us see the permutation idea visually. We rotate the variables forward by 1 position. Here is the list A, B, C, up to K, and on the right the rotated list B, C, up to K. And then a example of a cyclic expression. The product A, B is cyclic in 2 variables A and B. Step 2. Example. Because the first cyclic permutation swaps A and B, and AB equals BA, the expression does not change. Example of a cyclic expression in 3 variables. The expression, open parenthesis, x minus y, close parenthesis, times, open parenthesis, y minus z, close parenthesis, times, open parenthesis, z minus x, close parenthesis, is cyclic in x, y, z. Step 3. Example. Under the first cyclic permutation, x goes to y goes to z, and z goes to x. The product simply rotates its factors and stays the same. Warning about non-cyclic expressions. If an expression is not cyclic in n variables, it may still be cyclic in a smaller set of variables. Step 4. Warning. We often test cyclic symmetry on the variables that actually appear in the expression. In this lesson, we will factor a fully symmetric cubic expression in 3 variables step by step, following a clean strategy. Use symmetry, group terms, and factor progressively. Here is our expression. We will also use a quick test. If the expression vanishes when y equals negative x, then x plus y is a factor. Let's begin. Because the expression is symmetric in x, y, and z, it is natural to test the factor x plus y by substituting y equals negative x. Notice that x squared y plus xy squared becomes negative x cubed plus x cubed, which is 0. The remaining terms with y replaced by negative x also cancel to 0, so the whole expression becomes 0. Therefore, x plus y is a factor. By symmetry, we will expect factors y plus c and z plus x as well, and we will derive them by grouping now. Step 1. Group terms to reveal common structure. We split 2xyz as xyz plus xyz, and arrange terms into two balanced groups that will share the same inner binomial after factoring. Step 2. Factor out z from the first group and x from the second group. This produces the same inner sum in both parts. Step 3. Factor the common binomial. We factor out the shared parentheses to get a product with z plus x. Step 4. Rearrange the inner part as a quadratic in y. Write it as y squared plus the sum x plus z times y plus xc, all multiplied by z plus x. Think of it exactly like a standard quadratic in the variable y. Step 5. Factor the quadratic. We need two terms whose product is xc and whose sum is x plus c. Those terms are x and z, so it factors as y plus x times y plus c. Therefore, the original symmetric expression factors neatly as left parenthesis y plus x right parenthesis times left parenthesis y plus c right parenthesis times left parenthesis z plus x right parenthesis. We are going to decide whether the given equality is an identity. The claim compares two expressions built from A, B, and C. Our strategy will be to use a symmetry check, also called a cyclicity or swapping test, and then confirm the conclusion with a quick numeric counterexample. Step 1. Check cyclicity in A and B. Look at the left side. A plus b minus c quantity cubed plus ab plus 2c quantity cubed. If we swap A and B, nothing changes because a plus b equals b plus a and ab equals ba. So the left side is cyclic or invariant under swapping A and B. Step 2. Check the right side. The right side is ab minus 2c quantity cubed plus a plus b plus c quantity cubed plus 3a squared bc. The key term is 3a squared bc. If we swap A and B, that becomes 3b squared ac, which in general is different from 3a squared bc. Therefore, the right side is not cyclic in A and B. Step 3. Conclusion from cyclicity. The left side is cyclic in A and B, but the right side is not. If the equality were an identity, swapping A and B would keep both sides equal for all values. Here that fails, so the equality cannot be an identity. Step 4. Confirm with a counterexample. Let it equal 1, B equal 2, and C equal 1. Now evaluate each side. The left side becomes 2 cubed plus 4 cubed, which is 8 plus 64 equals 72. The right side becomes 0 cubed plus 4 cubed plus 6, which is 0 plus 64 plus 6 equals 70. Since 72 is not equal to 70, the equality fails for these values, confirming it is not an identity. We will factor the symmetric expression x minus y to the fifth plus y minus c to the fifth plus z minus x to the fifth. We will follow a clean 4-step structure and finish with the compact closed form. Step 1. Since if x equals y, the entire sum becomes 0, x minus y is a factor. Because the expression is cyclic and symmetric in the variables, the full cubic factor must be x minus y times y minus c times c minus x. Let us record this rule. Set x equal to y on the left side. We get 0, so x minus y divides the expression. By the same reasoning, y minus c and z minus x are factors, so their product divides the expression. Step 2. We now write the factorization in the standard symmetric form, the cubic factor multiplied by a quadratic symmetric expression. This gives the template with two unknown coefficients, a and b. Step 3. Determine the coefficient a. Equate the coefficients of terms of degree 5 in a single variable with one other variable, for example the x to the fourth y terms, on both sides of the identity. This gives a equals 5. On both sides of the identity. This gives a equals 5. Let us record this result. Step 4. Determine the coefficient b by substituting convenient values. For example, x equals 2, y equals 1, z equals 0. We will compute the left side and the right side and solve. We'll compute the left side and the right side and solve for b. Final factorization. With a equals 5 and b equals negative 5, we obtain the compact identity. This is a standard cyclic factorization of fifth powers. Final factorization. we are going to factor a beautiful symmetric expression step by step, following the exact structure and logic from the prompt. Our goal is to factor the expression 4 times the quantity x squared plus x y plus y squared, all cubed minus 27x squared y squared times the quantity x plus y squared. Step 1. The expression is symmetric in x and y. That means if we swap x and y everywhere, the expression remains unchanged. Let's visually swap x and y to confirm symmetry. Step 2. Factorization by roots. If the expression becomes 0 when y equals x, then the factor x minus y divides the expression. In our case, due to symmetry and how the 0 appears, we will capture it as a square factor. Substitute y equals x. The quantity x squared plus x, y plus y squared becomes 3x squared, and the quantity x plus y becomes 2x. We get 4 times the quantity 3x squared cubed minus 27x squared times x squared times the quantity 2x squared. That is 108x to the 6th minus 108x to the 6th, which is 0. So, the expression is divisible by the square of x minus y. Step 3. A second root line. If x equals negative 2y, plug in and check. Then x squared plus x, y plus y squared becomes 3y squared, and x plus y becomes negative y, so the square is y squared. We get 4 times 27y to the 6th minus 27 times 4y to the 6th, which is 0. Therefore, the expression is divisible by the square of x plus 2y. Step 4. A third root line. If y equals negative 2x, plug in and check similarly. By symmetry, x squared plus y squared again becomes 3x squared, and x plus y becomes negative x, so the square is x squared. The two large terms match and cancel to 0. Therefore, the expression is also divisible by the square of y plus 2x. To build intuition, let's see these root lines in the xy plane. The lines are y equals x, y equals negative 2x, and y equals negative 1/2 x. These are exactly the lines defined by the factors x minus y, y plus 2x, and x plus 2y, respectively. Now, we have found 3 distinct root lines through the origin. The expression is homogeneous of degree 6, and by the structure of these symmetric roots, the factorization compresses into a perfect square of 3 linear factors. Therefore, the final factorization is a equals the square of the product the quantity x plus 2y times the quantity 2x plus y times the quantity x minus y. In this lesson, we will prove a beautiful symmetric identity step by step. Then we will use symmetry and a clever substitution, propose a factored form, and finally pin down the constant by matching coefficients. Step 1. Rule: symmetry and substitution. We try setting it equal to negative b. Because the expression is symmetric in a, b, and c, if it equals negative b, the expression becomes 0. And by symmetry, it also vanishes for b equals negative c, and for c equals negative a. So the whole expression is divisible by each factor a plus b, b plus c, and c plus a. Step 2. Rule: propose a factorization form. Since the expression is divisible by a plus b, b plus c, and c plus, we write f equals lambda times a plus b plus c times c plus a. Step 3. Rule: expand and equate coefficients. We will expand both sides and compare the coefficient of the mixed term a squared b. First, expand the left side. Then subtract a cubed, b cubed, and c cubed. Next, expand the product on the right. The coefficient of a squared b on the left is 3, while on the right it is lambda times 1. Therefore, lambda equals 3. Therefore, the identity is proven. The expression equals 3 times a plus b plus c times c plus a. In this video, we will factor the expression x plus y plus z to the 5th minus x to the 5th minus y to the 5th minus z to the 5th. We will follow a clean 3-step plan. Use symmetry to find the divisor, choose a simple factorization form, and then determine the constants by plugging in easy values. Step 1. Because the expression is symmetric in x, y, and z, and because setting x equal to negative, y makes the whole expression 0, the expression must be divisible by x plus y. By symmetry, it is also divisible by y plus z, and by z plus x. Let's demonstrate x equal to negative y quickly. If x plus y is 0, then x plus y plus c is just z. and the expression simplifies to z to the fifth minus x to the fifth minus y to the fifth minus c to the fifth. That collapses to negative x to the fifth minus y to the fifth. And with x equal to negative y, we get negative y to the fifth minus y to the fifth, which equals 0. Therefore, a natural factor is the product left parentheses x plus y right parentheses, left parentheses y plus c right parentheses, and left parentheses z plus x right parentheses. Step 2. Because of symmetry and homogeneity, we assume M has the form A times the sum of squares plus B times the sum of pairwise products. So we write the factorization as the product x plus y times y plus c times c plus x multiplied by times x squared plus y squared plus c squared plus b times xy plus yz plus cx. Step 3. We will plug in simple values to find a and b. First, set x equal to 1, y equal to 1, and z equal to 1. On the left side, 3 to the fifth minus 3 gives 240. On the right side, x plus y, y plus c, and z plus x all equal 2, so their product is 8. The bracket becomes 3 times a plus 3 times b. So 8 multiplied by 3, a plus 3, b equals 240, which gives a plus b equals 10. Now, set x equal to 1, y equal to 1, and z equal to 0. The left side is 2 to the fifth minus 2 equals 30. On the right, the product is 2, and the bracket is 2a plus b. So 2 times left bracket equals 30, which gives 2a plus b equals 15. Solving the system, a plus b equals 10, and 2a plus b equals 15 gives a equals 5, and b equals 5. Therefore, our final factorization is 5 times the product, x plus y, y plus c, and z plus x, times the bracket x squared, plus y squared plus c squared, plus x, y plus yz plus cx. Thank you for watching. Don't forget to like, subscribe, and hit the bell icon for more math lessons. NENOMATICA, where mathematics meets YouTube excellence.